to the next episode of Let's Code Commodore PET using the Oscar 64 C++ compiler, and it supports quite a lot of machines that use the 6502 or derivate processors like the C64 and of course the PET, which we'll be targeting. This game will be like the traditional Snake game, like you know, perhaps from the old Nokia, not smartphones, dumb phones, or a million other variants, because it is relatively easy to do and works very fine on a text-only display. The game will be of such a size that it will not run on the 8 kilobyte machines. At least when I tried, it couldn't place the heap section because the program got too large. Mainly due to the printf routines, I think, because printf is actually a pretty complicated thing. We could work around that, but I'm just too lazy. So we'll target anything with 16 kilobytes or above, which is, I think, still quite a small requirement. If you want to install the Oscar 64 compiler, make sure to use the latest version. And for this particular example, targeting the PET, you actually need my implementation of go-to-xy, because that is actually broken in the current release. It might have been fixed at some point. I'm not sure if my pull request will get accepted, because I'm perhaps not doing it the right way, because my 6502 assembly foo is not that great, and either way, I basically copied this from the CC65 compiler, which is also quite nice, but has quite a bunch of drawbacks, only supporting ANSI C, and we can use modern C and maybe even C++ instead. So some C++ features like inline or in function declarations that you usually had to put at the start of the function, and many other things. So this compiler is still very much in development, so there might be issues cropping up. I submitted a couple of bugs myself, which Dr. Mortal Wombat, the author, fixes quite quickly. He's very much doing great work maintaining this compiler. Yeah, but if you want to play along at home, make sure to go to my repository, root42. Let's see, where are my repositories? Your projects. Oh my goodness. Oh, here, repositories, and there's a fork, Oscar 64, and I have a special branch at the moment. In the future, hopefully, something like this will be merged, called Detect Basic and Go-to-XY for PET. It's only the fix the Go-to-XY part anymore, which lets us place the text cursor anywhere on the screen to do printf as we like. Otherwise, that won't be possible. The implementation that is being used at the time in Oscar 64 is just the kernel call from the C64, and that doesn't exist on the PET, so everything crashes. So if you use this branch, it will work fine. Otherwise, you could, of course, implement your own print and go-to-xy routines yourself as kind of like a homework, and also that would work. But doing printing of numbers is a different thing indeed. We will start with the main function, with the main loops, and we will have two 8-bit variables, and you should always take care to use 8 bits whenever possible, because that's the fastest computations on the 6502, being an 8-bit processor. And we will have one called done, which we'll initialize with 0 or false, and one called quit, which we also initialize with 0. And this variable will be one when the game is over. Basically, you lost your life. And quit will be one if the user decides that he doesn't want to play any more games anymore. That's basically our two exit variables, so to speak. Then we will have one variable for key presses, for the quit routine basically. Then we will turn off the text cursor, otherwise it's blinking around and annoying the player. So that's defined in con.eo.h, and that's actually a function that works just fine. Then we'll have a function called draw intro screen, which draws just some instructions and the name of the game, which we'll do in a second. Next up is our main loop, which is looking at the quit variable. So while we are not quitting, we'll do the main loop of the game basically. But if we are quitting, then we'll go to the bottom of the screen, somewhere like here. 24 is the 25th line actually, it's 0 indexed, so that's fine. And we'll print something like press any key to quit. And then read from the keyboard, and then we'll just clear the screen and bail out of the program. That's fine. Okay. While we're not quitting, we are always setting up a new game. So setup game. And we'll probably want a semicolon there. And then we'll do the game, which is just a main loop. While not done, we are gonna do the following. We will first print the current score, which increases every time you make a step and don't die, and every time you pick up food. Food is worth 100 points, but we'll do that in a second, and every step is worth 1 point. I think that's a fair thing to do. Then we'll update the position of the snake, and it will check if we die because we hit the wall or we hit our body. And then it will return -1, which means game over. So we're done. And then we will make the game wait a little bit using the timer that is built into the pad. There's a 60 Hz timer, which you can use by using the clock function. That is actually standard C. And if we quit and the user has hit like a bunch of keys before dying, we'll do a clearing of the buffer, which can be done by doing while keyboard hit get character, which eats up all the extra keys, just to make sure that we don't get any spurious key presses. Then we also go at the bottom of the screen and ask the user if he wants to play another game. Another game? Yes or no? Something like that. And then we need, let's call this here C. We'll do something like C equals get character. While C is not equal to, now we have to use the Petsky literal. This gives us the Petsky literal, otherwise we would have to make a translation. The keyboard, when you press Y, returns Y in the Petsky representation. And C is also not equal to Petsky representation of N. So the user can only press Y or N for yes and no. So if C equals the N key, then we'll do quit equals 1. Otherwise, we will reset the done variable to 0 so that a new game can start. And that's actually already everything we need in the main function. Now we can start implementing all the other functions from top to bottom, I would say. So let's start with draw intro screen. The draw into screen function is relatively simple. It will clear the screen and then it will draw a box around what we want to say, and the draw box routine will come up in a minute as well. We'll go to 9,9, which is 10th column and 10th row, somewhere sort of middle in the screen, 20 wide, 10 high. That gives us a pretty much centered, roughly centered box, and we will use our PETSCI to screen routine to draw a border, and we'll go up here and define what that border will look like. And looking up in the PETSCI table, we find that hexadecimal A6 is a pretty nice checkerboard patterned block, basically, which is not too bright. It's like half bright, and I think that's a pretty neat thing to draw the border with, and we will also use it for the snake body probably. And I think we forgot a parenthesis here. Yes. Then we'll go into the box 10,11 and print the title of our game like so, which is 1, 2, 3, 4, and then snake, and 5 spaces in the end, I think, because we have 18 spaces in total. Then we'll go down by 2 to 10, 13, and we can copy that whole stuff, and we'll write something along the lines of by root 42. You can of course write your own name. I give you permission to do that for your own copy of the game, and some minimalistic instruction, namely we tell the user to use WASD keys, just like Doom or any other game where you can move around. W will be up, A left, S down, and D right, because the pad has only very annoying cursor keys, which you have to use Shift to use in parts. So let's use WASD, that's much better. Then we'll go to 17. And I just noticed that I have a little typo in my notes, because there I had 10, 15. But okay, that's how it goes. And we say here, press any key. So that's not quite centered. Let's take one space away here. And that should roughly do the trick. If we say press any key, we should also wait for a key press. So we do this with get character. Now, if we want to use this, we need the drawbox routine. I prepared it here, and let's do that. Let's implement drawbox. It's actually pretty simple. It takes X and Y position, a width, a height, and a character to plot. So we'll do something like if character, no, sorry, for, I was in the PETSCI routine, for int I equals X, I less than X plus the width, we'll increment I, and then we'll plot something on the top row, basically, that we specified. The X coordinate will just be counted up. The Y coordinate will stay the same, and we will plot our character. And then we can copy this, and we will draw the bottom line, basically. So Y plus H minus 1, very important. Otherwise it will get too large. And then we can copy the whole block for the vertical bars, and that will be y plus H. And here we will have the X coordinate that will stay the same, similar with the width, and the Y coordinate will be counted up. So this will draw the left vertical line of the box, and this will draw the right vertical line. And now you ask, well, how does the plot function work? We'll do a little macro for this. So plot will take x, y, and z arguments, and it will write to the screen, which we'll define in a second, at position whatever y was, times the width of the screen, which is 40. This will break on 80 column displays, but that's okay. We are only targeting 40 column paths here. We can do some magic to avoid that, but right now this will only work on 40 column things, so make sure to set that up in your Vice, or if you have a real Commodore like 8016, 8032 or something, feel free to change this. It's easy enough. You can also write a screen detection where you put the 40 here into a variable. Note that the multiplication is pretty expensive, but since this is static here times 40, the compiler will probably optimize it. And the boxes will be drawn only once at the beginning of the game. So it doesn't matter too much if the multiplication is expensive, because the 6502 doesn't have a multiplication unit. You have to basically make a loop with additions on the assembler level. And that's of course bad. So we will cast this to unsigned integer and write that to that screen position. Okay. Then we need to define screen, but that's a unsigned char. We can actually use uint8t. Screen equals oh, I need to cast this to uint8t as well. And it's at location 0x 8000 hexadecimal basically. So that's our pointer to the screen, and we can just write to it. At least that's the first screen page. I think there might be multiple screen pages, not sure, but we're using only one because we don't need double buffering or anything. Alright, that's pretty neat, I would say. The drawbox routine is done. The setup game routine is next, I think. So we'll go into setup game. The setup game routine has to do a couple of things. First of all, it will also clear the screen to get rid of the box we drew before. Then it will set the random number generator with a seed due to the current clock, so you get a different game every time you run another game. In the emulator, this will be probably always the same game in the beginning, because the clock will be always the same after rebooting and dropping in the program or disk image. So don't be worried about that, but once you rerun the game, it will look different. And on real hardware, it always matters how fast you load the game, how quickly you type, so that will be always very random. So yeah, given that, I think that's good enough for us. Then we'll have some variables to set up. One is called snake begin, which is set to, well, what do we set it to? Let's say we set it to 2. Because there will be a circular buffer, something for the X and Y positions with different cells. Let's say this is the X position of the snake, and the snake will begin, let's say, at position 0, 1, and 2. So on the screen, this snake will be on these X positions, first column, second column, third column. And then when the snake moves, it will move further to the third column, and the last column needs to be erased, sort of. We won't do the erasing in the array that we store the coordinates in, but we will use that information that is in here to erase the last block. So we don't have to draw the snake all the time, but we only have to draw the head of the snake and we have to erase the tail of the snake. Except if it eats food, then it gets longer. If this is not quite clear now, it will become clear in a second, I hope. The snake end will be at 0 in our array, and the snake length will be 3, 0, 1, and 2. So we need to declare those things, and I need to shut down my code completion again and this thing, otherwise you get too much errors. And yeah, we'll do it just like so. These are also 8-bit variables, because the snake can be not very long, otherwise it gets very, very hard indeed. But you can play around with these variables to make it longer. We start out with a snake of length 3, which is fine, I think. We'll also draw the snake now. I equals 0, I less than snake length, plus plus I. That's it. And how do you want to do this? Basically, at the beginning here, we can just say, okay, snake x at position I is equal to, let's position it at x position 18 plus I, so it will be roughly center of screen, and y position will be 12, also roughly in the middle of the screen, and we'll also plot the snake, snake x of j, comma snake y of j, comma snake body, and we need to also define snake body, and we'll do that right now. And I would say we reuse the border character, but you can use a different one if you want to give the snake a different look. You could also use different elements if you wanted to. And then we need a snake speed, which is the number of frames that we halt the game between steps. 20 will be like 3 steps per second on a 60 Hertz screen. We also need a score. Also, this should be an equal. Snake score will be 0 at the beginning, obviously. We need a direction that the snake moves in, and we'll take direction x is 1 and direction y is 0. The snake can only move horizontally or vertically, and it's moving to the right now. Then we need another box which marks our screen, which will be starting at the top left, and we'll go across the whole screen using our border element. And then we will drop some new food so that we have something to eat for the snake. There's a bunch of variables that are still missing. Snake speed. Snake speed. Let's copy this, and direction. So let's copy this here and put that in front of everything. And we could already initialize it up here, but once we do a new game, it will be with the wrong value. So we do it only in the setup game. Okay, that's a good setup. But drop new food is still missing. Drop new food is relatively simple, but the food should be random and it must not land on a part of the snake. So what we'll do here is create a variable food x position and food y position, and we will do some random drawing while wherever we place the food, and we will need a get macro very soon. Food y is not equal to an empty space, basically. And here we don't need the Petsky screen code stuff because the space character is actually quite correct. And what do we do if we not land on a free spot? We will do food x equals 1 because we don't want to land on the border, which is row and column 0, plus some random value, logical and 38, which limits everything to column 1 to 39, which is outside of the border that we drew. And for food y, it is the very same thing. And here it's 23 because we have 25 lines. And the 0th and the 24th are border again. And if we've done that, we will call plot on food x and food y using the food character. So we need to define get and food. We will define food as being the 0 character, which is the @ symbol on the screen, which is a nice food symbol, I would say. It looks like an apple or something, or some fruit, I don't know, with a little bit of imagination. Then we need the get function, which is again a macro for performance reasons, and that's actually pretty simple. Let's see if we need a cast maybe. We're just taking the screen value at this position, and I think this is just fine. Yeah, that should do it. We're not writing, so we're just evaluating screen at position x and y on a 40 column screen. Same limitations apply if you're playing on an 80 column device. That will not work correctly. All right, pretty good. There are only 3 more things left. And namely that is the print score, update game and wait game. So let's do print score first because that is actually pretty simple, as we have the go to xy function already. And print score will just go to column 2, row 0. So we write into the border, which should look reasonably nice, hopefully. And we write something like score %u and be done with it. And that's the snake score. Let's double check if we defined it. Yeah, up here we have snake score. That's good. Next up is update snake. Update snake is a more complex function. The update snake routine is the main game logic of the game. And here we at first check if the user pressed any key. We use the keyboard hit function for that. And if that is the case, we read from the keyboard using the get character function. And then switch to use a switch statement to select what action actually needs to be taken. And as I said before, the cases here have to use the Petsky encoding for the key. Like, for example, as we're using WASD, we can do something like this. W is the vertical direction we want to go up. So if the direction in if the direction y is not equal to 0, because we're already going either up or down, we will ignore this key, so it doesn't do anything. Otherwise we might, for example, run straight back into the snake, which would be, I think, not very wise. But if that is not the case, we will set the x direction to 0, because we were running horizontally before. And we'll set the y direction to -1, because that's upwards, basically. And that's it. And this block we can copy a bunch of times, 4 times to be precise. Let's take A for left, S for down, and D for right. A meaning left will be an X direction, and we will go left and stop movement in the vertical. With S it is a down direction, so we just have to change this. And D going right is X direction will be 1 and Y direction will be 0. And that's it. And we'll also add a possibility to stop the current game, which I think is the run stop key, if I'm correct. That should be key number hexadecimal 12. Then we should do a return -1. That's the tab key on the emulation keyboard, basically. And I think that should be the run stop key. Not 100% sure, but at least in the emulator you can press tab and be done with the game. Case 0 means there was no key press, in theory, but we only go into this if there's a key press. So actually we can leave that out. If we detect anything else, we just do nothing. Let's put a comment here. No or unknown key. It's do nothing. Okay. Now we need to update the snake. We know which direction it is going to move now. So we need to have the old X position that the snake was moving in, which is just snake X, snake begin. As I said, we have two arrays where we store the individual segments of the snake, and we need to actually define that, and let's very quickly do that. It is called snake X and snake Y, and this has to have a maximum size, basically. Let me check my notes. We call this snake buff for buffer. That's where we store the snake. And I will pull up the... did I copy that? Yes. I will copy all, move all the definitions here a further bit up, even the macros. Okay, there we go. That's nicer. So snake X and snake Y store the positions of the snake body. And we first pick up where the old X position was. And then we compute the new position, which we call new X, and that is old X plus direction in X. And the same for the new Y position. It's old Y plus dear Y. And then first we need to check if we hit the boundaries. So if new X is smaller than 1, or new X is greater than 38, or new Y is smaller than 1, or new Y is greater than 23, then we hit the boundary and we return -1, which kills the snake. Then we get the object that is in front of the snake. So that is a get with new X, comma new Y. And if the object is food, so an add symbol, then the snake will grow. We'll do that in a second. Else if the object equals snake body. We also could have tested here for like the border, but then we have a problem with the score section, for example, so it's better to check for the coordinates. But for the snake body, it's, I think, easier to do this instead of looking to the snake buffer, which might be very slow. So we just check if the object in front of us is a part of our body. Then we kill the snake and the game is over. And else? Well, else we can update the snake position. which means the new snake end will be advanced one. So we could write snake end +1. However, this is a circular buffer. Once the snake buffer reaches the end after like 127 moves, it will have to wrap around. And this wrap around can be done in two different ways. You can either do a modulo operation with snake buff, that is the 128, but the modulo is a division, so it's very expensive. Instead we do an bitwise AND. However, then we need to use snake buff -1, which gives us 7 ones in binary, so that will be 1, 2, 3, 4, 5, 6, 7. So if we go from 127 to 128, that would be, let's see, let's write this down. Oh, I shouldn't have used too much spaces. This will be as follows. So this is 127 plus 1 will be 10000. And if we do the AND operation with this here, it will lead to 0. So it will be a correct wraparound, so to speak. Okay, this is a very fast operation. This is a decrement basically, or it could be also computed by the compiler because it's a constant expression. So that should be really, really fast. Okay, let's talk about food. If we hit a food, we increment the snake score by score food increment, and you can define that however you like, but I'm going to use 100 here. Whoops. Let's go back down. And after that, if the snake length is already its maximum length, and I think we have to define that, then snake end will become exactly that. We just copy that. Else we increment the snake length, and we have now consumed some food, so we have to drop new food somewhere on the screen. And also every time we eat food, the snake gets stronger. So if the snake speed is still greater than 5, we will decrement the speed, which is the number of frames that we wait. And I think we're missing a couple of things now. I think the snake max length is missing. So let's define that as well. Snake speed we already have. Let me check my notes. Snake max length is actually a const. Let's make that const. Oh, not this one. This one here. And I put that at 126 just for giggles. We could make it up to 128 in size, but I wanted to be sure that I don't read any weird stuff at the end. I think 127 is the maximum because we need 1 at the front to override. And actually 1 at the back to erase. So I think 126 is truly the maximum that we can use. Anyway, I think that should be it. Let's indent this. So we got the food covered, we got the body covered, we got regular stuff covered. So snake begin and snake end are updated, and the snake will creep across the screen, sort of. But the snake begin is not yet updated, so we need to do that. Snake begin will become snake snake begin +1. the next item in the buffer basically, and we need to do the wraparound again, so it's the same as with the snake end. And we need to update the snake X and Y arrays. So snake X of snake begin is new X, and the Y coordinate is the same. Good. Also, this means we have done another step, so we will increment the snake score by score step increment, which we'll need to define. Then we need to draw the snake, draw snake, and we return 1 because the snake is still alive. The snake score, score step increment, and here I'll give 1 point for each movement that you survived in the game, which is I think fair. That's that. Last function actually, the draw snake routine. That is actually rather simple. First of all, we need to figure out where the old end of the snake was. Old end. And that is the snake end -1. And here we need to do the wraparound. If the snake end was pointing at 0, it needs to point at 127. So we again do the logical AND with a snake buffer length -1. That should work. Then we plot the snake, the new snake head, which is snake of X indexed by snake begin, and snake Y indexed with snake begin, and we use the snake body obviously. And then we can do we can erase the snake tail by indexing with the snake arrays with old end, and we're not using snake body, but instead we're using a blank space, and we don't need to convert anything because it's the same. So let's quickly check. We've got our defines, we got our macros, we got the screen, we got the game global variables, the game state basically. Would be nice to have this in a struct somewhere, but for such a simple game I'm just skipping it. We have the petSCHI to screen conversion routine, we have the draw box routine, the print score, we have drawing the snake, which draws the head and erases the tail. We've got a function to drop new food and draw it on the screen. We have the update snake, which is the main game logic, reacting to the key presses, updating the snake position, killing the snake if necessary, and collecting the food, increasing the score and dropping new food, and then updating the snake and drawing it. The setup game sets up all the global variables, plots the initial snake. Very simple. Oh, the wait game. That is pretty important. Otherwise, it will be very, very fast. Yeah, let's do that. The wait game function is actually rather simple. We have a starting clock, which is a long integer. And we'll set this to clock. It's the current ticks, basically, that have elapsed since the computer was turned on. And while the current clock minus start clock, obviously, is smaller than snake speed, we will wait, just wait. So what this does is start clock will be equal to clock more or less in the first iteration of this while loop, because this is only incremented every 50th or 60th of a second. And once a 50th or 60th of a second has elapsed, clock will increment, and this will get larger, so to speak. It starts out as 0, then will turn to 1, etc. And snake speed at the beginning is, I think, 20 or something. What did we set it to? Where's the initialization? Snake speed is 20, yeah. So after roughly a third of a second, it will have elapsed. Where is here's the wait game function. And yeah, this will quit the while loop and everything will be fine. So we can now compile this. We can now compile this by using this command line here. Oscar64 has to be in your path, so make sure to set the path accordingly. We'll use optimization level 1 because there's still one bug in the Oscar as of writing or of recording if you optimize too heavily, but you can even run without optimization, so it will be fast enough. Our target machine is a pet with 16 kilobytes. Output will be snake.prg from snake.c. And we've got a couple of errors that we need to fix that I probably put in while typing this. Okay, error, array type expected. Oh yes. There needs to be the asterisk at this point. That's better. Score step increase. Did we? Oh yeah, we mistyped. Let's correct that. There are some unknown identifiers, so probably just some index errors. Oh yes, this has to be an I instead of a J, and that should almost be it. 172. Ah yes, I pressed some key there. And 224, which is a missing semicolon. Classic. There is still a warning about a constant getting truncated. Let's try with optimizations. Okay, so it's complaining in which maybe it's correct. Oh yes, it's actually correct. So we need to make this signed integers. Yeah, that works. And I wanted to show you that even without optimizations, the game is just fine. Then we open up our Finder, and there is the new snake.prg, and let's have a look. Okay, snake by root42, use WASD keys, press any key. Oh, I need to click in the window. Oh, and the snake body is still wrong. Okay, we need to convert that to screen codes, basically, but we can already check if this works. Now the snake is larger, and the right key doesn't work, so we probably have another issue there. Two things to fix. First of all, the snake body is actually at the moment a PETSCII code, which we need to convert to screen code. And let's do this manually, and I already tell you snake body will be hexadecimal 66. Otherwise we have to call PETSCII to screen all the time. Quite a lot, but we already know that it's always the same thing. So let's use this. Then we have a problem with the right direction. Question is, oh yeah, it was that I forgot the if dir y is not equal to 0 has to be a dir x is not equal to 0. Okay, let's fix that and do that again. Left, down, right. Yeah, this is looking great. So the game works. Let's see, yeah, the snake eats its food. You can see the score incremented by 100, and every step we get one more score. Ah, there is still something broken because the score has to be bigger. So there's an issue. We have an 8-bit score, which is pretty lame. I think we can safely say that probably no one will go beyond 65,000 points. And if they do, good luck to them. The end of the game routine doesn't respond to any presses except if you press Y. Let's just crash into the wall right here. And if you press no, it says press any key to quit, and it will quit. So that's pretty neat. And let's try this again. Let's see if the score now can go beyond 128 or something. Or 255 to be precise, probably. It's a bit slow at the start, but I'm not sure if we want to make it really fast. Otherwise we don't have so much room for making it faster. Yeah, the score has now reached 290, so that seems to be fine. Now we have a score of 400 because we ate something. Let's see how far we can take the snake today. And I think it plays actually pretty well. Not bad at all. Okay, now it's getting visibly faster. And yeah, I think that's already it. I will show off the game on the real machine in a minute, in the outro basically. But yeah, please leave some comments, like and subscribe as usual. I hope to see you in the next video, and maybe you can fork this project. It will be on Codeberg, link in the video description, so you can try it out yourself. The Oscar compiler is steadily progressing. I hope it gets even better. It is already quite usable and a lot of bugs have been fixed, so I think that's pretty nice. And now the game is getting actually relatively hard. But that's it for today. Thank you very much and see you in the next video.